Alright, this is hour 2 of Physics 1C for August 27th. Everyone's working on this problem right here that you can see on the screen. Yeah, there you go, Tyler. That makes sense. For people watching on YouTube, do people are just kind of writing their answers into the chat? We'll discuss here in a second. Has that been enough time for most people to at least set it up? Whether you did the final calculation or not, it's okay. Does anyone want to... Yeah, where's my chat overlay? If you guys want to work on... I mean, I can put it into the OBS, probably. I probably should. Okay, a lot of people getting the same answer. So the answer that I'm seeing a lot of people get is that it's x equal to 0.775 meters. And does anybody want to tell me how'd you start it to get it going? Like, what was kind of your idea? How you did it? You set Coulomb's law equal. That's exactly right. We know that the place where the net force is equal to 0 is the place where these two forces are equal to each other. So that means that F23 has to be equal to F13 in terms of its magnitude. And the F23 is basically just K times Q2 times Q3, which we don't know, divided by the distance between them squared. But if you look at the picture, Q2 and Q3 are separated by a distance of x, so that's just x squared. And then for the force between 1 and 3, it's going to be K times Q1 times Q3, because it's 1, 3. And we divide that by the distance between these two guys, which is 2 minus x squared. You need to square the whole thing, of course. And that's 2 meters right there, but just for clarity, I'm not going to put it in there, because this is mostly just math from here. And you just start canceling stuff, you know? Just cancel, 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 cancel. You asked me if you had to put the microcoulombs, and the one thing I didn't want to say is, once you actually put this in microcoulombs and this in microcoulombs, the micros cancel out as well, right? And ultimately, you end up getting a quadratic out of this. You got to square this and multiply, but you will get eventually x equal to. I think that's the right answer. I mean, I've done this problem a lot, but that looks like a familiar answer to me. Yeah. So there you go. You know, the arrow means do all the algebra until you find out what x is, basically. So, yeah. Alrighty. Anyone have any questions before we move on to something just a little bit more challenging? Hidden within this problem is something that's really important, and it's kind of contained within this picture right here. Chapter 23. Yeah, let me just check real quick. I thought it was 22. It's 21. We're in chapter 21 right now. 23 on survey, 21 from university. Yep, that's right. Yeah, the 23. These are examples from survey because I'll just show you why I'm using the examples from survey real quick. So, okay, yeah, this is an example of one of the ones from university physics. They have these strange artifacts from the PDF conversion process, and they just look really junky. So if wherever possible, I'm not going to be using the things from university physics, but we will be doing problems from there too. Also, like the problems in Survey are generally, this is the key thing. The problems in Survey are much closer to the level of difficulty of the homework problems from university physics. Does that make sense? It doesn't matter which one you read because the book itself, both books are really similar in terms of material, Ash. But I like Survey better personally. Personally, I like Survey better. So it doesn't mean university physics is bad. It's my personal preference. Okay, so we did this one. Any questions at all? Where's my mouse? Okay, now we're gonna do one where we're gonna have to do something a little more complicated. Everything's in a straight line in this problem, right? But there's something that's contained within this problem that's really important to understand. So when I have a particle that's subject to more than one force, right? To find the total force on the particle, you do the vector sum of all the forces, right? Superposition, the principle of superposition, exactly. That applies for these forces just as it did in Physics 1A. Okay, so the next problem we're going to do is one where we have to do superposition of forces, but they're kind of at an angle, so we can deal with some trick here and get you kind of accustomed with how that's going to happen. What I think I'm going to do is I'm probably going to show you the steps of how to do this one, and then you'll be able to kind of use similar ideas for another problem that we're going to do. So in this problem it says, consider 3-point charges that are located at the corners of a right triangle. So I've got a positive charge here, positive here, a negative charge here. The values are given here. Q1 and Q3 are the same. They're both 5 microcoulombs. And then Q2 is -2 microcoulombs. And then the distance A, it's a right triangle that's isosceles. It's like the same on both sides, is 0.1 meters. We want to find the resultant force exerted on Q3. And if you are looking at the book for this problem, there's some vectors that are drawn in that I removed here so I can have you guys actually think about it. Okay. Give you guys a second to read it. Alright, so you guys tell me, if I came to this location here and I wanted to draw the force created by the negative charge Q2 on Q3, what direction would I draw the arrow? Would I draw it this way, that way, left, right? So that's going to be the force. Oops, we're going to modify it a little bit. That force right there would be the force that we're going to call F of, it's 2 on 3, right? So that's going to be my notation, 2, 3 here. Now let's do the same thing for the positive charge. I'm going to come to this point right here and say the positive charge Q1 exerts a force on Q3. It goes away from Q1. That's exactly right. That's right. So it's going to need to go kind of this way. I'm gonna fix this here as well. Put it just right there at the center. Now I'm going to scale this one, and you guys tell me how to scale it. Which one of these two vectors is going to be bigger? Can you figure it out in your head which one's bigger by looking at the numbers? The second one. It's farther away, though, too, right? Keep that in mind. Right? It's farther away. So we're kind of have to see with the calculations, but I think you're probably right. This is 5 and this is 5, so in the numerator you're going to get a 25, right? This one's 2 and 5, so numerator 10. The denominator for this one's 1. The denominator for this one's going to be that number squared, so it's 2. So 25 divided by 2 versus 10. So they're actually pretty close to each other, as it turns out. But you're correct that this one is a little bit bigger. All right. It's going to be kind of a ratio of 12.5 to 10, or 1.25 to 1. This is going to be about 25% longer. Did I make it that much longer? I don't know. I just kind of... this is the force of then 1 on 2. So to do these problems, in my opinion, what you really want to do is just find the values of these first, and then worry about directions later. Right? So what's F23 going to be? Ah, thank you. It's 1 on 3. Thanks. My bad. That's confusing. Should be 1 on 3. Yep. So let's just find the values of the forces themselves. So F of 2 on 3, and you guys can start calculating this if you want, is going to be our symbol K, which is just, I'm just going to immediately put in numbers since this is kind of a plug and chug kind of thing. Put a little bit of units in there too. So F of 2 on 3, we're going to do Q2 times Q3. So that's going to be, I'm not going to worry about the negative sign when I do this. Okay, it's going to be 2 microcoulombs. And we'll actually write out what micro is. So 2 times 10 to the negative 6. And then we're going to get 5 times 10 to the negative 6 for the other one. Coulomb. And we're dividing that by the distance between the two of them. A was 0.1, so it's going to be 0.1 meters squared. Can you guys calculate that for me? I want to do so as well. I got 9 million. Does that sound right to you guys? What do you guys think? Cool. All right, same thing for the other one. It's going to be really similar. In fact, it's so similar that what we're going to do is we're just going to take this whole thing, we're going to copy it, paste it down here, and just drag it up here. And we'll just go in and change some numbers. So let's go. This should work. So now between 1 and 3, it's going to be 5 and 5, right? So I can get rid of the 2 and plug in here 5 and the times. And then in addition, in the denominator here, we're going to need to erase that guy and do 0.1. It's multiplied by root 2, right? So it's 0.1 root 2. Whoops. No, don't do that. 0.1 times the square root of 2 meters squared. And that one is going to be so I get like 11.25 times 10 to the 6th. You got 8.02? Did I do it wrong? Do other people agree? Okay, cool. If you have a problem, oh my god, why does it do that? Well, I gotta figure out what stroke I'm doing that does that. If you have a problem dealing with the exponentials, it can. Oh, you've already got the final answer. All right, fair enough. That's good. All right, so you can just multiply the coefficients, right? 5 times 9. Divide by this thing down here, and then do all the exponents at the end if you want to. So, all right. Oh, it's not. I'm an idiot. Oh my god, what is it doing? Is it because it's inside the... Yeah, it is. Here. All right. Gosh, no way. I don't know if I mean... Look, there we go. This is the part I want to get rid of, though. There we go. The 10 to the 6th. You guys are right. It's divide by 1,000 and I multiply by 1,000. It's 9 and 11.25, right? Okay. All right. So those are the right answers, right? Okay. What do we need to do now to combine these two? Vector addition. Yep. And how do we do vector addition? Trig, yeah, right? We need to find the angle up here. Yep. All right, the angle's pretty easy to find, though. What's the angle going to be? This angle is... Yep. All right, so we know the angle is 45 degrees. We just need to break F13 up into components. So we can basically say we can have some component, F13, we want the x component. That one should just be equal to F13, which is 11.25. Multiplied by cos 45, and since it's cos 45, they're going to be the same, right? So F13Y, I'll write it like this. This would be 11.25 sine 45. And then this one only points in the kind of x direction. So I would say that if I add up all the forces acting in the x direction on my object, what I'm going to get is that 11.25, whoops, 11.25 times the cosine of 45. That one's pointing, that's going to point, like, there's going to be a component this way, right? And there's going to be another component this way. This is F13x. So I need to subtract F23, right? So minus 9. There we go. Minus 9 newtons. And then if we add up the forces in the y direction, we're going to get this just the 11.245. 11.25 sine 45. What do you guys get for these numbers? So I get like 8 and -1. So this one ends up being about -1 newtons. And this one ends up being about 8 newtons. Which means that the force, the total force acting on this object, say the sum of all forces, is just going to be equal to -1 I hat plus 8 j hat, approximately. And that's going to have newtons as the unit. -1.045. Yeah, that's what I got too. -1.045, and then about 8 for the other one. So that's one way to write it. Or, of course, you can also do the thing where you find the magnitude of the force by square root of 1 squared plus 8 squared. And that's in newtons again, and that's going to be equal to, I assume, 8.02, which is what Ty got earlier. Does that sound right to you guys? And then if I want to find the angle that's made by the total force, you would just do the arctan of 8 over -1. Don't really worry about the negative sign. We kind of know that the net force acting on this object now, it's 8.1, right? So I'm going to put it in a different color. The net force now, it kind of points up 8 units, right? And then over 1 unit. So kind of like that, basically. A little bit like that, at least. I need to move this around a little bit. Something like, maybe like that-ish. Ooh. Oh my god. No. Oh boy. What on earth did I do? I pushed Control Z and that didn't fix it. Oh no, we're okay. We're okay. Okay, yeah. Anyway. Yeah, drawing on the diagram I can see causes some problems. Anyway, and then whatever this is equal to. You actually, this is going to give you an answer that doesn't make any sense. You got to get rid of the negative sign. The answer you get out of arctan of 8 over 1 is going to be 83 degrees. But that's going to be like above negative x-axis, right? Or it would be 180 minus this, which would be, what, like 97? Counterclockwise away from the positive x-axis. God, this stuff gets met the moment you introduce trig. These problems get a lot more complicated, right? But what I want to emphasize is that you're all good enough at trig to do this stuff. You're all good enough at algebra to do this stuff. The only new thing with what we're doing now is just the positive and the negative charges. Why do you say okay like that? What does that mean? You don't feel like you're good enough at trig? I mean, it's not like it's easy. I'm not saying. Oh, algebra's really hard. Yeah, absolutely. I think the algebra is usually the harder part. Definitely. And that never really stops with physics courses. Some of the most difficult algebra that I did was when I took my physics courses. Like, it's That's the way it goes. Okay, any general questions? I think this is the last problem with Coulomb's law that we're going to do. And for the last hour of the class, we're going to talk about electric fields. So, yeah. This would kind of be more like there, I think. Because we're adding together this vector. Okay, so let's take another 10-minute break. We'll start again at, let me stop the recording.